Okay, this is the section 7.2, right triangle trigonometry, notes to go along with the online trig class. We need to define some things like we always do at the beginning of each section, and then we will work through some examples. So the word trigonometry essentially comes from the Greek words of trigonon, meaning triangle, and the Greek word metron, meaning measure. Using a right angle, which is 90 degrees, both the angles and sides of a right triangle can be measured. Recall that the side opposite the right angle is called the hypotenuse. So if you're wanting to label that on this picture over here, it would be the side C, because that is the one that is across from the 90-degree angle. So in this picture right here, let me label this with the word hype for hypotenuse. And then that means that the other two parts of this triangle, the ones that actually form the right angle, are called the legs. Now, in a minute, we'll talk about a geometry concept that you might remember about right triangles. So let angle theta, be an acute angle in this right triangle. So it can't be the 90-degree angle, so it either has to be this angle down here or the one at the top. We are referencing the one at the bottom right now. Then the words sine, cosine, tangent, cosecant, secant, and cotangent will describe relationships between the angle theta and ratios of these three sides. So we're going to define those ratios right below. And most people have maybe heard this phrase, at least maybe once. One of the ways that we remember this is by a phrase called Sohcahtoa. So I'm going to write that right here. Sohcahtoa. So let's go down and fill in what that means. So sine, which is S, is actually opposite over hypotenuse. And for us, since this is my theta right here, opposite means the side across from theta. So this would be B. The hypotenuse is C. Cosine means the adjacent side, so A and then hypotenuse, so over hypotenuse. And cosine is the side that is actually connected to the angle we're referencing, that is a leg, so it has to be a leg. So that would be A over C, which is our hypotenuse. Tangent refers to the opposite leg over the adjacent leg, so that would be B over A. Now, something interesting is that cosecant, secant, and cotangent are just reciprocals of these individual trig functions that we've defined above. So cosecant is hypotenuse over opposite, so that means it's C over B. Secant is hypotenuse over adjacent, which would be C over A. And cotangent is adjacent over opposite, so that would be A over B. This is exhausting all the different ways that we could take those three sides of a triangle and put them into ratios of a numerator over a denominator. So notice a lot of students have troubles remembering which ones are the reciprocals of each other, which ones get flipped. It does not match up with the letters, so you have to be careful there. Sine and cosecant, cosine and secant, and tangent and cotangent. Those individual pairs are the reciprocals. Now, we're going to do some examples. So find the values of the trig functions of the acute angles. So we're going to find all 6 trig functions if we know that the adjacent to the angle, that side has a length of 12. So that means that that one is 12. The side opposite the angle has a length of 5. That's all we know so far. And then this is where you have to remember something from geometry class. If you have a right triangle, you have a theorem that says in a right triangle, the two legs squared and then added together equals the hypotenuse squared. So that is a squared plus b squared equals c squared. So we're going to use that to help us find c. So that's our part B right here. So a is 12, 12 squared, plus we know b is 5, and we don't know c. 12 times 12 is 144. 5 times 5 is 25. Add those two together, that's 169. And then we would want to take the square root of that to find c. So the square root of 169 is 13. So that means our hypotenuse is 13. And the hypotenuse should always be the longest side in the triangle, so that does make sense. Now that we know all three of our sides, we should be able to write all of our trig functions. So, and when you write them, it's very important that you write the angle you're referencing as well. So sine of theta, that's our argument, equals opposite over hypotenuse, so that would be 5 over 13. Cosine of theta is adjacent to the angle, so that would be adjacent to the angle over hypotenuse, so that's 12 over 13. And tangent of theta is opposite over adjacent, so that would be 5 over 12. Once you have the first three, you know the others by the reciprocals. So this would be that cosecant is 13 over 5. Secant of theta is 13 over 12. And cotangent of theta is 12 over 5. Something very important that a lot of students take a while to understand about trig functions. Functions usually have an input and an output. When you're talking about a trig function, the input is the reference angle we're looking at, and the output is the ratio of the sides. So which ones of these ratios are reciprocals of each other? We've already seen that sine theta and cosecant theta are reciprocals. Cosine theta and secant theta are reciprocals, and tangent theta and cotangent theta are reciprocals of each other. And that's stated on the next line of this notes in a little chart here that says if you need cosecant, secant, or cotangent, just remember that it's the reciprocal of these. So in other words, they're showing that they've divided by that, which means you're really just flipping the fraction. Something else to note though, tangent, remember, is opposite over adjacent. If you think about it, that's the same thing as sine over cosine. And the reason for that is sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. If you were to flip this and multiply by the reciprocal, O over H times H over A, that cancels out the H's, so you just get O over A. So that's where this comes from. So tangent theta is actually sine over cosine, which means cotangent is cosine over sine. And we'll use that in our next example to help us find tangent. So given sine of theta is square root of 10 over 10, and cosine of theta is 3 over the square root of 10, or 3 square root of 10 over 10, find the rest of the trig functions. So I always like to write down the ones that I know, and the ones that I don't know I leave a space for. So I don't know tangent yet. I don't know cosecant. I don't know secant. And I don't know cotangent. Excuse me. Using this quotient identity right here, I can find tangent by putting sine over cosine. So square root of 10 over 10 divided by 3 square root of 10 over 10. Anytime you have a fraction over a fraction, you really multiply by the reciprocal of the bottom. And that would be 10 over 3 square root of 10. The 10s cancel out, the square root of 10s cancel out, and you notice you have a bottom number of a 3. So this is a top number of 1 left over 3, so it's actually 1/3. For cosecant, you just have to flip this, and we get into trouble here. We are not allowed to leave radicals in our denominator, so we have to rationalize that, and that's something that you may or may not remember how to do, so we're going to walk through it. We need to create a perfect square down here. If you times a square root by itself, that creates a perfect square. Whatever you do to the bottom of a fraction, you have to also do to the top. So this becomes 10 square root of 10 over the square root of 100. The square root of 100 is 10. So notice the 10s are going to cancel, and the answer to this one is just square root of 10. We also are going to have to flip cosine to get secant, so 10 over 3 square root of 10. Again, we need to get rid of that square root of 10 in the bottom, so we're multiplying top and bottom both by square root of 10. and that would give me 3 times the square root of 100 on the bottom. That would be 10 square root of 10 over 3 times 10. The 10s are going to cancel because they're both outside, and so it would be square root of 10 over just 3. So that one is our secant. So I'm going to circle all of the answers. This was given, we found tangent, we found cosecant, we found secant, and remember cotangent's just reversing or flipping tangent, so it's just going to be 3 over 1 or just 3. Using the Pythagorean theorem, we can also come up with one more identity. These are called our fundamental identities, the reciprocal properties, the definitions essentially of our trig functions, and then this is a really crucial one. If you think about this, remember in our triangle, so I'm just going to redraw a picture of a triangle. We had our hypotenuse, we had our theta, we referenced it here, we had our adjacent side and our opposite side. Pythagorean theorem is a squared plus b squared equals c squared. If you were to divide everything by c squared, essentially we're dividing it so that we can get a 1 over here. Notice that this right here, a squared divided by c squared, is the same thing as a over c squared. Because both parts are being squared, you could actually write the squared on the outside. Same thing here. But a over c is adjacent over hyp, which means that a over c is cosine of our theta. So this would be cosine of theta squared. And then b over c is opposite over hypotenuse, which means that that is our sine of theta. Now, they rewrote this in a different order down here, and that's fine. They just kind of wrote it so that it looks like the property that we have. Excuse me. So sine theta squared plus cosine squared equals 1. And notice that there is a change in the notation right here. This 2 is on the outside, the squared part. In trig, we write it right here. That does not mean that the theta is not also part of this. This is just the notation we use in trigonometry. So sine squared theta actually means you have a sine with a theta evaluated in there, and then you square it. So it's just how we use the notation. So this is called the Pythagorean identity. Now there are 2 other variations of this same identity, and they are found by just manipulating the one we just came up with. If you divide everything in this by sine squared, in other words, you're just trying to see what would happen if we tried to turn one of the things on this side into a 1. Well, sine squared over sine squared would be 1. Cosine squared over sine squared is cotangent. And 1 over sine is the reciprocal of sine. So that's actually, remember, cosecant. So that's how they come up with this variation of the formula. To get the other variation that involves tangent, we divide everything by cosine. In other words, we make this term 1. So we're just trying to manipulate this to see that we can use the other trig functions too. So sine over cosine is tangent of theta. Cosine over cosine would be 1. Because they're both squared, so they match, and 1 over cosine squared would be secant squared. Oop, I see. So that's how they came up with this formula. So we're going to look at our example number 3. Find the exact value of each expression. Do not use a calculator. This says 1 over cosecant squared of 35 degrees plus cosine squared of 35 degrees. Well, a lot of people are like, well, I don't know what cosine of 35 degrees is. Well, sometimes things are actually a lot simpler than they look if you use your identities. So 1 over cosecant is kind of throwing me off. I like to change things back to sine or cosine or tangent if I can. So cosecant, remember, is the reciprocal of sine. So this would actually become sine squared of 35 degrees plus cosine squared of 35 degrees. And the 35 degrees now doesn't matter at all, because anytime we have sine squared plus cosine squared, we just learned that that equals 1. So no matter what these 2 degrees were, if this is sine squared plus cosine squared, the ratios attached to these and then squaring them and adding them together will always equal 1. Okay, so let's look at this one. This one's a little bit funny. Cosine over sine is cotangent. Oops, I wrote cosine. Talking and thinking sometimes doesn't work with writing. Of pi over 3, and then we're subtracting it from itself. So it's the same exact thing, so that actually is going to equal 0. So sometimes by putting things in weirder or different formats, changing the format, you can actually evaluate without using a calculator at all. Okay, this next one, example 4, we're going to solve it 2 different ways just to show you that there's multiple ways you could approach these problems. So it says, find the values of the remaining trig functions given the values of one of them. And we know that sine theta is 2 over 5, and it's an acute angle. So that means that it's obviously not referencing the right angle part. So if I make this my theta, sine says it's opposite over hypotenuse. So opposite of theta is 2. Hypotenuse is over here across from 90. If you want to use the definition and find the other trig functions, you're going to have to find this missing side. So essentially we have to do Pythagorean Theorem. So this would be a squared would be x squared plus b squared, and this time we already know the hypotenuse, which is 5 squared. So x squared plus 2 times 2 is 4, 5 times 5 is 25, subtract the 4 over, that's 21, and then we take the square root of that. So x down here is square root of 21. Now that we have that, we should be able to find the rest of the trig functions, because all we need is to create the correct ratios. So I'm just writing down a spot for each one. So sine we already knew was 2/5, that was given to us. Cosine is adjacent over hypotenuse, so that's square root of 21 over 5. Tangent is opposite over adjacent, so that's 2 over the square root of 21. We are going to have to rationalize that. The nice thing is when you multiply something times itself, when it's a radical, the bottom just ends up being that number. So it's 2 square root of 21 over 21. Cosecant we just flip, so that'd be 5/2. Here we'd get 5 over the square root of 21, so we have to rationalize by multiplying top and bottom by square root of 21. So that's 5 square root of 21 over 21. And on this one, I would not flip the final result. I would go back to the original. It was 2 over square root of 21, so if you flip it, it's just square root of 21 over 2, and therefore you don't have to worry about rationalizing anything. So there's my 6 ratios using Pythagorean Theorem and our definitions of Sohcahtoa and the reciprocals. So for this next one, it says, let's find it using the identities. So we know that if we have sine of theta being 2/5, let's try doing it with the Pythagorean identity. Let's see what that finds for us. So sine squared plus cosine squared equals 1. This will help us find cosine. So this would be 2/5 squared, because remember, this whole thing is being squared, even though that notation is written like that, because sine theta is 2/5. I don't know cosine squared theta. And this may be a little bit too advanced for us right now. Well, I think we're going to have to do this a different way. Maybe not. We might be okay. So then we would have to subtract this over. Anytime you have 1, you can make it any number over itself. So I'm going to make it 25 over 25 so that I can subtract. Yeah, we're going to be okay. And then this would be 21 over 25. And because this is squared, we need to take a square root of both sides. So cosine theta. Now where you have to be careful here, and the reason I said this might be a little advanced at this point, we haven't really discussed the fact that when you take a square root, you're supposed to put a plus or minus. Since we're not dealing with quadrants yet, it doesn't really matter. But once we start talking about how things are located on the x and y axis, that will be important. So I officially like doing it with the Pythagorean theorem. That's just my personal preference. So I get square root of 21 over 5, which is what we got earlier with the other one. And then we can use the fact that tangent theta, this is another identity, is sine theta over cosine theta. So this is 2/5 over square root of 21 over 5. You could just times top and bottom by 5. That clears out those fractions. So that tells me that tan theta is 2 over the square root of 21, which we already learned we had to rationalize. And that gives us the 2 square root of 21 over 21. And then we would just need to flip all for the other 3. So that part doesn't change. So it's just really what preference do you want? Do you want to use Pythagorean theorem with just the numbers? Do you want to plug into the Pythagorean identity or to one of the other identities if you know enough pieces? So there's multiple ways that you can approach these. Okay, our last set of notes or page for 7.2 is over complementary angles. So we're going to discover what is a complementary angle first. So it says find the ratios given below for the following figures. Sine of B. Big B is our angle here, so capital B. So that would be opposite, which opposite from that would be little b, over hypotenuse, which is C. Cosine of B would be adjacent over hypotenuse, so that would be little a over C. Sine of big A, now you have to be careful here, this is this angle up here. When we do that, this is now opposite, so that would be little a, and hypotenuse is still C. And cosine of big A is adjacent, which is connected to it, and it's a leg over hypotenuse. So notice that sine of capital B, which is this angle, so I'm going to reference that with color, is equal to not sine of the other one, but cosine of A. So the sine of this angle is the cosine of this angle. If you think about it, that makes sense because in a right triangle, we learned that all angles in a triangle sum to 180 degrees. That's another fact from geometry class. So if this is 90 degrees, that means these have to add up to 90 degrees. So there's a complementary relationship there. And also cosine of B, so we'll record that with the yellow angle, is sine of A. Record that with the blue angle. So that's just an interesting fact that we've discovered. So because of this relationship, sine and cosine are called complementary to each other. In addition, a similar relationship exists with tangent and cotangent and cosecant and secant. Oh, excuse me, I had to pause for a second. I had a cough. I call these complements. I didn't write that in there. So why are these ratios equivalent? And, oops, sorry, minimized. What is the relationship between angles A and B? It's because the angles have to add up to 90 degrees, which makes them complementary angles. Complementary angles is a pair of angles that have to add up to 90 degrees. If you remember supplementary angles, that's another word you might remember from geometry, those had to add up to 180. So this is just kind of pulling back some of those old skills. So complementary angle theorem says that the complements of complementary angles are equal. Okay, so what we're wanting to say here is that what would this be equal to? We're not actually going to be evaluating it yet. So since this is sine, and we know that sine's complement is cosine, we really have to think about what angle goes here, though, because if sine is 35, so say this referencing this angle, The other angle we're going to be referencing when we say that it's equal to a cosine has to be over here. So 90 minus 35 is 55. So this would be the relationship. Sine of 35 degrees is the same thing as cosine of 55 degrees. Pi over 3, you have to remember what that references. If you want, you can convert that to an angle if that helps you. So remember, multiply it by 180 over pi. That is 60 degrees. So that means that to make this complementary, we'd have to be talking about a 30-degree angle because that would add to 90 degrees. And then I would want it in radians since they used radians. So 30 times pi over 180, we have to do it the opposite way to go backwards, is pi over 6. So tangent would be cotangent of pi over 6. Again, we're going to have to think about this in terms of here. Pi over 12, let's think about what is that in degrees. That's sometimes easier when you first start doing these. That would be the pi's cancel, and 12 and 180 are both divisible by 6. So that would be 2 and 30. And actually this will go again, so 2 goes into itself 1 and 30 15 times. So this looks like it's just 15 degrees. So the opposite of 15 degrees when we think about adding up to 90 degrees would be 75 degrees, and we'll want to turn that back into radians. So that would be 75 pi over 180, and I'm going to have to divide that by probably 15, I'm thinking, to reduce it. Let's check and see if that works. Yeah, that would be 12 on the bottom, and 75 divided by 15 is 5. So this would be secant. Remember, its complement is cosecant, and it would be of 5 pi over 12. Notice that this, if you add these two angles together, that makes 6 pi over 12, which is pi over 2. Pi over 2 is also 90 degrees. So that's kind of interesting. Remember, that should add up to 90 degrees as well. So it does in radians as well. And then our final examples, excuse me, find the exact value of each expression. Do not use a calculator. Okay, so what we know is that tangent of 75 degrees, well, cotangent is, remember, the complement of that guy. And when we want to change him to his complement, we have to figure out what would make this add up to 90 degrees. So tangent of 75, actually. These two, remember, are equal to each other because they are complementary angle measurements because it adds up to 90, and these are the complementary trig functions of each other. So this is actually the same thing over itself, so the answer again is 1. For this one, you could go either way. You can convert sine to cosine or cosine to sine. Let's do sine to cosine. So remember, to convert it to cosine, you have to remember that you're using the other angle in that 90-degree triangle. So 90 minus 52 is 38. So this is actually cosine of 38 degrees as well. Because remember, these are equivalent when you change this part to its complement and you make sure you use the complementary angle. So this actually equals 0. All right, and that ends the section 7.2 notes.